So, good morning, one and all, and welcome to the Net Zero Technology Centre's Tech20 session for this week. My name is Roger Esson. I'm the Head of Industry and Partner Network here at the Net Zero Technology Centre, and I'll be your host for today's online event. Tech20, for those of you who perhaps haven't joined us before, is our series of social showcases for speakers presenting technology-focused themes in 20 minutes or less. Thanks for joining us on the webinar today. But before we kick off the presentation, just a few housekeeping things to deal with. These events are called Tech20 because we split them into 20-minute blocks. So you'll hear from our guest speaker today for around 20 minutes. With 20 minutes for Q&A, and then at the end of the session, 20 minutes to network with some of the other attendees. Two options for asking questions. You can either raise your virtual hand and I'll come to you at the end of the presentation, or you can use the chat function. And as we go during the presentation, if there's anything that you think of, please put them into the chat function and I'll come to you and ask you whether you're willing to ask the question yourself. We want to make this session as engaging as possible for both you and our speaker, so if you are willing to speak, please do so. We'll try to get through as many of the questions as we can in the 20 minutes, and if you do comment on social media, please use our hashtags, #Tech20 or #Time2Tech20. So, without more ado, let me introduce our speaker for today. Professor John Irvine has made a unique and world-leading contribution to the science of energy materials, especially fuel cells, energy conversion technologies, with his work being internationally recognised. Highlights of John's activities include discovery of the emergent nanomaterials phenomenon, establishing the field of oxide fuel electrodes, delivering high-performance direct carbon fuel cells, and demonstration of significant hydride ion conductivity. I'm not sure if he's going to cover some of that in his presentation, but today's presentation covers the subject of ammonia fuel cells. I noticed that Ella Booth has joined us. Hello, Ella. Ella was one of our interns last summer who actually did her summer project on ammonia. So welcome, Ella, and hopefully you will have a question at the end of this for John. So without any more ado, John, over to you. If you'd just like to introduce yourself and give us a little bit of an overview about your presentation.
Hi, welcome everybody. Good morning. My name is John Irvine. I'm from the University of St Andrews, and I'm also CEO of a startup company called Zero Emission Fuels, and we've been doing some work recently looking at applying ammonia to marine shipping, and I'll tell you a little bit about that as we go through.
Excellent, thank you very much. So John, over to you. Your 20 minutes start now.
Okay, 20 minutes or less, we'll see. So just to start with, I'll look a little bit about renewable energy and green fuels, and then about ammonia, and finally our application of ammonia as a marine fuel. So some of you may not realize, but if you go to the east Nook of Fife, there's quite a lot of wind, and there's something like 5 gigawatts being proposed on our doorstep. Half a gigawatt is already being, but and the NNG is going to be online within 12 months probably. So we've got a lot of electricity that probably we don't quite know what to do with, and producing hydrogen is a really important aspect of that, and it's something that Scotland can do and should do. So we talk about being at 100%, have 100% renewable capacity for electric. We've moved on a little bit from that, thank goodness, but if you just take that at face value, if you've got 30% availability, it means you need 3 times the capacity that you would normally have, that you would need for your maximum to be reasonably confident that you might be able to supply the grid. That means you need fossil nuclear redundancy, otherwise the lights go out. Now, if you use renewables to meet non-electrical needs, it removes a lot of redundancy, because you can justify more renewable generation, and so you can cover your energy needs, and that brings out energy devolution, which is really the realization that energy is not just electricity. It's only a quarter to a third of our needs are electrical. There's transport, there's chemicals, and there's heat. And in particular, transport and chemicals are great opportunities. Heat is an important problem. It's the lowest cost value, and I think we always need to pay attention to heat. But that's the final thing we address if we create new technologies. It's not going to pay for new technologies, but it's really important that we keep that engaged. So hydrogen is a very good fuel. As an element, it's got the highest gravimetric energy density, but practically it's rather hard to compress, and it's not anything like as good as something like diesel. But if you use a liquid carrier, such as ammonia or methanol or synthetic hydrocarbons, you can carry the hydrogen and move it around very readily. So if you can use hydrogen locally, use hydrogen. If you need to transport a lot of hydrogen, think very carefully about carriers. So ammonia is very interesting. If we use clean energy to produce chemicals, you have to remember that currently we've got a fossil fuel economy, and fossil chemical industries are still there. For example, if we make ammonia, we need hydrogen, and that could be grey, brown, or blue, which is coming from gas or coal, and that's very carbon intensive unless we somehow manage to install carbon capture. But more importantly, it's very economically intensive. There's a huge capital nested in these production systems. So say for producing ammonia, it's very hard to make green ammonia competitive with ammonia from grey or brown hydrogen, just because all that capital has been invested, and the chemical companies need to recoup that. So the price of ammonia, because it's done at scale, because the capital is already there, is quite low and quite challenging, and that's why renewable ammonia is not so common. In fact, if you convert ammonia to hydrogen, you'll produce hydrogen at a much lower cost than you can buy the hydrogen. Now, things are changing though, and in the last year or so, with gas prices going up and up, fertilizer prices and ammonia prices have gone through the roof. So tripling of fertilizer prices until about January 22. And I'm sure you're all aware that some things are happening that are going to make this even more challenging for fossil ammonia, fossil fuels generally, and the war in Ukraine is only going to increase prices further. So could we use renewable power to produce ammonia? Well, actually, we used to. 100 years ago in Norway, Norsk Hydro produced their ammonia from hydro, and they had two electrolyzer plants over 50, 60 years of over 100 megawatts each. So this is renewable hydrogen, and that was the main source of ammonia until it got priced back by natural gas, and there's still something like 5% of global ammonia production is through renewable hydrogen. So in summary, ammonia is one of the most important industrial chemicals. It's widely used in agriculture as a fertilizer for food production. Conventionally, it's produced at very large scale using fossil energy sources. So we need to be able to address that. Historically, produced using hydrogen produced from hydropower. It's a paper from Nature Geoscience a few years ago, but it basically says that the world's population is twice what it would be if it wasn't for the Haber-Bosch process producing cheap ammonia and cheap fertilizer. They reckon that you'd have half as many people could be sustained if we didn't have ammonia. And you might argue that maybe we don't want twice as many people, but the problem is we do have twice as many people and we need to feed them. So ammonia is really important and a really important part. Now, you can also use ammonia for energy, and it's a really good carrier for hydrogen, as I suggested earlier on. It's about 17% by mass, but you can liquefy it at low pressure, and you can move it around. So it just takes hydrogen to a slightly higher scale and a bit more movable, but it's perhaps best viewed as a hydrogen carrier. So you can produce hydrogen. Ideally, you might use renewable energy to produce the ammonia direct from this. You can get heat and power, which we'll look at, and then you can use the hydrogen or the ammonia for hydrogen transport. So that takes us to ZEM and a recent Department for Transport project that just finished a few weeks ago, where we're trying to prove direct ammonia fuel cells for maritime propulsion. And the partners were at the University of St Andrews, Low Emissions Resources Global, were based in Dundee and produced the fuel cells, and Port of Cromarty, Firth, who helped us very well to engage with market opportunity. So fossil fuel driven shipping is responsible for up to 5% of carbon emissions. There's legislation to decarbonise maritime by 2050. Ammonia is emerging as the leading candidate for fueling a new low carbon maritime economy. We would suggest electrochemical conversion is more efficient than burning. You avoid nitrogen oxygen production. You probably have twice as an efficient system. And if you can use the ammonia directly rather than cracking it and then using the hydrogen, you just produce water and hydrogen, no NOx. Hopefully, you need to make sure there's no ammonia slippage, and you get electric power. You'll note from the ship on the side that it's not just CO2 that shipping emits. There's a lot of sulfur oxides and nitrogen oxides, and there's very strong legislation to mitigate against that. Probably even more pressing than CO2. And again, fuel cell technologies really help to remove those emissions. So the market volume is about 50,000 large ships per annum, with 30 billion, but there's a lot of small ships and boats that could use ammonia as well. The amount of goods transported by sea is increasing, so actually the amount of carbon dioxide produced in maritime transport is likely to increase if we don't improve technologies. And as other technologies become less CO2 intensive, then maritime becomes, the percentage of CO2 emissions from maritime becomes really serious. So just to introduce the idea, and we'll come back to look at these in a little bit more detail. Our idea is to put ammonia into a direct fuel cell based on an alkaline oxide. Ammonia goes down the center, air goes around the outside, and we generate power. And you have a lab-based cell on the right, with about 5 centimeters long, that we utilized. So the concept again is to use a protoconducting ceramic working at about 600, 700 degrees centigrade. The ammonia cracks in situ to produce hydrogen and nitrogen. The hydrogen is oxidized, and that yields water after the hydrogen ions have moved through the electrolyte. And just to update on progress, so this was the results from the EFT project that we recently completed. So the first thing is making the cells, and that's with Lurgan and the University of St Andrews. And these are the sort of tubular cells that one makes. So they tend to be measured in inches because of the US background. So that these are up to 10, 20 inches long, and they're made by extrusion. And we've characterized these at St Andrews, and very, very important is the microstructure of the electrolytes. These are protoconducting electrolytes. There's quite a bit of IP around these, a lot of it dating back to early work at St Andrews. And we've used these in testing in the lab in the small cells, and we ran 500 hours testing, and with no real loss in performance. So they're very resistant to degradation. Small increase in performance, perhaps due to perhaps electrode reduction, but not essentially everything was stable and nothing to panic about. Very worried about slippage. If you convert 90% of the ammonia and 10% escapes, that's really bad for atmospheric pollution. You might worry about the AdBlue in people's cars. You might wonder why there's more ammonia in cities at the moment. But if you're going to have an ammonia fueled system, you need to either catalytically remove the ammonia through a slip catalyst, or you need to have a system that doesn't produce any ammonia. And if you see here that all the black points, which are at 600 degrees centigrade, we could detect no ammonia being produced. And that was actually independent of where we were passing current or not. So the ammonia was cracking in situ. It should crack at 600, but you need a catalyst to make sure it goes through to completion. And the cells that we're doing are catalytically very active for that. Looking at testing, this was a short project, so we were really very happy to get any results at all. So it was a 6-month project, and this is where we've been looking at the fuel cell testing. It's ammonia going up the center, and then air being fed over that. And these are larger cells. These are working up to 8 watts, 8 to 10 watts each cell. And we see that, you know, even at utilization of 60% of the hydrogen, I guess you could say 60% of the fuel, but all ammonia is cracked to produce hydrogen. So 60% of the hydrogen is converted in the first pass through the fuel cell. You'd obviously want to engineer a number of cells to you had all the hydrogen converted, and that worked at different utilizations, different temperatures, up to 250 hours on this cell. And then comparing ammonia with nitrogen hydrogen mix of similar composition, found we got pretty much the same performance. And then finally we started working on cell bundle development, so working on 3 cells to start with. And here we were able to get 15 watts per cell, and in the last few weeks we've got 30 watts per cell. So to get a kilowatt we need 30 of these cells, which is pretty achievable. And our next stages of development are to build these up. So there are lots of places where you could use ammonia as a fuel on farm, but in the marine sector, it's really hard to find something to replace marine diesel oil. And then I think most people are looking at methanol or ammonia as the liquid fuels of choice. I'm not so keen on combusting these because you end up producing CO2 from methanol. But in either ammonia or hydrogen engines, you have to be very careful about the NOx production because they're quite high temperature engines. So unless you change the catalytic cleanup, you will end up producing NOx from these systems. So it needs to be engineered in. If you use a fuel cell, the temperature is too low and it takes too long to pass, so you don't get the NOx formed. Especially when you use a protoconductor, when the oxygen is on a different side to nitrogen. So so this is sort of a service vessel that might be a good place to look for early application of ammonia fuel cells. And if we look at the markets, things like diving boats, fishing boats, cruise ships and ferries, you have to show technologies at an achievable scale. And whilst it'd be nice to replace oil tanker or ammonia tanker systems with ammonia propulsion, I think one needs to prove that the technology works at a smaller scale first. And the most attractive applications for the next phase of our development are auxiliary power and stationary power generation. So it could be cold ironing port side to charge the batteries on vessels, or we've had a lot of traction in looking at doing demonstrations on board. So supplying the auxiliary power unit with ammonia. So say a 1 kilowatt ammonia fuel cell and a 5 kilowatt battery. That will give you your heating, your shipping, run your electronics. It'll be quiet. There's no engine running, just a small air pump, and perfectly good for auxiliary power, especially when you're sitting in the harbour with the engine switched off. And yeah, just finally, our next target for the next phase of the project, we hope will be launched shortly by Department of Transport, is to look at putting this into a small experimental vessel, a scientific support vessel, and that's looking pretty positive in terms of engagement. So we're hoping to move on to that, and just our support from Department of Transport, Scottish Maritime Trust cluster, and going forward with the Net Zero Technology Centre. So thank you for your attention.
Thank you very much, John. Great overview of the opportunity there in ammonia. And Ella, I will be coming to you, so you have been warned. I'm coming to you for a specific question, as you were one of the people with specific knowledge on this. But I guess, John, from my perspective, just to kick things off, are we moving quickly enough looking at ammonia here in the UK, or are we lagging behind other parts of the world at the moment?
I think it's not just ammonia, we're generally lagging behind the rest of the world at the moment. We're talking quite strongly about the big picture, but actually the enabling steps we're not doing quickly enough. And I've been going on about ammonia for probably 20 years. The possibility of producing ammonia on farm has always been a real challenge, and it is addressing the disparity in cost between fossil fuels and green fuels. It's becoming a lot easier now for all the wrong reasons, but I think it's really important.
Thanks very much. So over to you, our attendees. I don't see anything in the Q&A at this moment in time, but there must be some questions out there from the audience. So now is your chance to chip in and ask the questions. Ella, coming to my rescue. Please unmute yourself and ask your question.
Hi, fantastic presentation. Thank you so much. The only thing I was just wondering about was the ammonia slip that you mentioned. I've only dealt with that in a kind of stationary sense, and I was just wondering if you're purely dealing with it with your catalyst choice, or if there was any other measures that you're kind of putting in place to prevent it.
Yeah, we don't. In some ways, we don't really need to have a catalyst, because the proton conductors are very basic materials, and they're very well suited to being ammonia cracking catalysts. So it's in the intrinsic nature of the fuel cell means it can also act as a cracking agent. I think there's a lot of concern that there should be in an AdBlue fueled vehicle, there should be an ammonia slip catalyst. The old story about Volkswagen playing with its figures and having really good performance in terms of miles per gallon and really low emissions, but not telling anybody that they weren't using the same conditions for the two tests. So I'm concerned that there's not enough ammonia slip catalysis being applied in all the vehicles we have, and most diesels now have this AdBlue, which is a solution of urea, and it works by decomposing into ammonia. which then removes the NOx in the emissions. If that's not quite tuned correctly, you're producing ammonia. So there certainly are ammonia slip catalysts. Ammonia is not stable at above 300, 400 degrees centigrade. It cracks naturally into nitrogen and hydrogen. So it just needs a catalyst just to make sure it splits. We've done a lot of work in university about trying to produce ammonia using these technologies, and you've got a big compromise between working at a high enough temperature to get the process to run and trying to make sure that the ammonia is stable by the time you finish producing it.
Fantastic, thank you so much.
Thanks very much for that, Ella. Richard Cowan, if you're willing to come in and ask your question, just come off mute and ask it. Otherwise, I'll just read it out.
Oh, yeah. Thanks very much for the wonderful talk. I was wondering if you thought there was a case for kind of temporarily switching marine diesel engines to something like 80 or 90% like co-firing of ammonia as a more rapid but temporary method of partially decarbonising the sector, or if you had any thoughts on that.
I think there's an opportunity. I mean, I guess that's partly where ZEM started, was looking at catalytic protection of the emissions. So mixing fuels and co-burning, like even I guess if you're mixing ammonia and fuel, you're essentially mixing hydrogen and nitrogen, because the temperatures are quite high in the engine, so it will decompose. But you have to remember that hydrogen will burn at a higher temperature than the diesel. So you need to address the catalytic cleanup on the outside to do that. But if you've done that, then I don't see any reason why it wouldn't work. So yeah, I think it can be done, but you need, if you just simply replace the diesel with hydrogen or with ammonia, that's dangerous. You could end up with a lot more air pollution. But if you take the added step and added the extra catalyst just to make sure everything was cleaned up, then there's no reason why it wouldn't work. And maybe why not even use a pure ammonia? I'm not much. It was used in Belgium in the 1940s to fuel vehicles because they couldn't get gasoline.
Great, thank you for that. Thank you, Richard. Johannes, again, if you're willing to, just come off mute and ask your question.
Yeah, if you can hear me okay. I was just wondering about the efficiency of the fuel cell that you have been looking at in comparison to LOHC technology. I mean, I'm not aware of any plans to use LOHC as a kind of fuel for marine applications, but in general, it would be also interesting to see it as a storage for hydrogen.
Yeah, in terms of efficiency, it's quite competitive. I guess one concern is there's a lot of redundant mass. So if you store hydrogen in ammonia, when you've used it, you're left with nothing. Whereas when you've taken the hydrogen out of the organic carriers, you're left with most of the molecule, and you need to regenerate that. So I think LOHC for bulk transport is where its strength would be. So if you're moving very large amounts of hydrogen, that may be the way, maybe where it has a real strong role. So I don't actually like excluding technologies and picking one and saying everything else is rubbish, because that's never true. There's usually sweet spots. And LOHC was initially proposed for bringing energy from Canada, from the hydros in Canada to Germany in probably the 1970s. And it was costed out on large tankers. Ammonia is probably much more competitive than methanol for that, because there's a lot of shipping of ammonia, and it's pretty shippable and people understand it. I think one of the other questioners leads to that as well. But I think for small, medium scale fuel and engine, I think the ammonia is certainly better than the LOHC, and if you were to use LOHC, you'd be looking at cracking it or decomposing it into producing hydrogen in situ, and that's probably better done centrally, actually, if I think about it. It's not quite my chemistry. When you get too many carbon atoms, I get a bit nervous.
Thanks, Johannes, for that question. John, I guess a couple of questions from me on the regulatory framework more than anything. I mean, the likes of DNV or the shipping side of things, are the regulations moving quickly enough to be able to, or is that going to hold up the deployment of ammonia as a marine fuel?
Most ammonia is already shipped on lorries or on vessels. So compared to high pressure hydrogen, you're probably you're really much more advanced. So the regulations would come to the application and not the storage. So there's a lot of information on bunkering out there. I think there's room for new technology just to make things a little bit safer. There's some magnesium chlorides that you can use to store ammonia quite readily, and that might, if you need a buffer between just to make sure you don't have ammonia release, and to be double sure on sensitive places, that might be a really good approach. But we haven't been looking at that, but there has been quite a bit of interest in those from Denmark. Initially as a hydrogen store, but I think as ammonia store, they work really well. So.
Okay, thank you. Stephen Livermore, again, if you're willing to, just come off mute and ask your question. Okay, I'll ask away. There are existing logistics mechanisms for ammonia in industry that have a good safety record. In moving to other areas like transport, how much work is going on around the safety aspects, particularly leakage from a vessel storage or land-based storage system?
So with our colleagues in Cromarty, we've been looking at the bunkering and understanding the bunkering. So getting the ammonia into bunkers, there's a lot of work going on that. I think we need to look quite carefully about, say, a calor gas cylinder of ammonia that you might use for an APU. I think that's where the demonstration project, a key part of the demonstration project is to make sure that could be done safely. I mean, ammonia used to be used for fridges in 40, 50 years ago. There's a lot to be learned from history in these things. But it was, I just tried to suggest we could use ammonia for an aircraft in an aircraft for some of the BA or somebody similar, and they were not terrifically keen because the sort of smell of ammonia in the cabin, creating a panic, was not really somewhere we wanted to go. So I think we're a lot better on marine applications where I think it's much better understood and accepted.
Excellent. Any more questions from anybody before we wrap up? I mean, I think the onshore part of it, and clearly the work that's going on with Port of Cromarty Firth. I mean, is there enough happening in the other ports and harbours up and down the coast, or is that going to be one of the blockers to widespread deployment?
I mean, I talked about the MARPOL regulations on sulfur and nitrogen emissions, and at present, I think most large shipping is illegal according to the international regulations, but it's not being enforced. If these CO2 rules are going to be enforced, we're going to need a methanol or ammonia fuel shipping within 5-10 years, and that's a massive change that has to be implemented. So there's no time, really. We've just got to address this. I guess obviously try to address it in a controlled and systematic way, rather than everyone trying a little bit and not making so much progress.
Excellent. Well, John, thank you very much for an informative presentation and for answering the questions, and thank you to the audience, the wider audience, for the questions that you've posted to John. So I'd just like to, on behalf of the NZTC and everybody, thank John for the presentation today. And we now move to the networking session. So if you would like to join us for the networking, if you stay on the call, we will upgrade you to a panelist, which will allow you to come in and to participate in the networking. Again, thanks to John, thanks to you for attending, and have a good weekend when it comes. Thanks very much, and bye-bye.